All right, so ionic bonds. This is going to be the very first part of the IGCSE bonding unit, and it's not that bad. Everybody's going to do really good on it because I'm going to make sure you all do really good on it. So this is the basic outline of what we're going to go through. We're going to review atoms, talk a little bit about ions, discuss Lewis dot, and then the idea of the stable octet. All right, so the atom. This should be a bit of a review. Just remember that the atom is the smallest complete unit of measurement of matter. What's most important is whenever you see the phrase atomic state, or if something tells you that it is, if the question ever tells you that this is an atom, what that really means is that it's neutral in charge, and that just means there's no overall charge. So for example, I would have equal number of protons and electrons. So if I have 7 protons and 7 electrons, that means there is no charge. There's an R in charge. You can think about it like math. If I have +7 and then a -7, these two things will end up equaling 0. It's just the idea that equal and opposites will cancel out. This is a sodium atom. I know that because I can count up the 11 electrons. I'm not going to do that for you. I'm sure you can do it on your own. But I do want to take a little bit of time to review this part. Remember, this would be these electrons are outside of the nucleus, and they are organized into energy levels or shells. So this would be the second energy level, first energy level, second energy level, and then this is the third, or what we would call the valence shell. This will become important later on in this little video, so keep that in mind. Remember, the valence shell is the outermost one. The reason why I know it's an atom is because there are 11 electrons and 11 protons. My protons are the positively charged ones, noted with a little plus sign. They're going to be the same number, so there's not more of one than the other. So there are equal number of electrons and protons. Therefore, they should cancel out in charge, making the atom neutral. All right, valence and shielding electrons. We talked about this a little bit on the last slide. So here we go again. This was covered in IGCSE last year. So this should also be a little bit of review, but I figured I'd go over it anyways because it is very important. Valence electrons. These are electrons on the highest energy level, or the outermost shell. You might have heard this a bunch of different ways. They are the farthest from the nucleus is a good way to think about it. And they're important because valence electrons are the only electrons that are generally used in bond formation. These are what make chemistry go, is a good way to think about it. And then there's really, I like to think about electrons in two different ways. There are valence electrons, the ones on the outside, and then there are shielding electrons. Shielding electrons are in the lower energy levels. So for example, if we were looking at the sodium from the last slide, the Na, there was one valence electron. That one that was on the outermost one, the outermost energy level. And then every other electron would have been a shielding electron because they were on the inside of the I don't know why my brain's not working right now. They were on the inner energy levels. That's what I'm trying to say. So there was one valence electron and 10 shielding electrons. Shielding electrons don't do much. They'll come into play later on, but for right now, don't worry about them. Okay, so a positive ion. This is a cation. Just like this is a great way to remember this. I'm going to give you a little phrase. Cats have paws. We can all agree on that. Kitty cats, they have paws. Yeah, they walk on paws. It's like their feet. Cation are positive. This is not the real way you spell positive, but it's a joke. It's a pun. Cats have paws. These are my little paws. Cations are positive. If you don't get the joke, I'll explain it to you later. It's actually super funny. You should all be laughing very hard right now. So what a cation is, it's just an atom that has lost one or more electrons. What that means then is there are more protons than electrons. So for example, if I have 7 protons and 6 electrons, I can see that there is one more proton than electron. So then this would have an overall positive charge. There are more positives than negatives. So those positives outweigh the negatives, and it's no longer neutral, it's positively charged. This would be an example of a sodium ion. Remember that the original atom, the sodium atom, had another electron sitting right there, but it lost that electron. It's gone because it gave it away. So when it loses an electron, there's now one more proton than electrons. I have 10 electrons and 11 protons, which means there is one more proton than electron. And I know that even by the symbol. So this is the symbol for the sodium ion. And it's showing us that there are more positives than negatives right there. That little plus in the upper right hand corner. This will give you the information you need. And you are also expected to include that when you are telling us something is an ion or an atom. We'll do practice with this later, don't worry. A negative ion, this is called an anion. Chemistry has a lot of definitions that are dualistic in nature, and I'm sure you guys, if you know what that means, good for you. Dualistic means two things that are opposites. So a coin has a dualistic nature. There's the face with the side with the face, and then there's the side with the number, opposites. So ions are dualistic. Ions can be positive or negative. There's one or the other. So a negative ion is going to be one where there are more electrons than protons. So this is an atom that has gained electrons. What you should be noticing is that when we are forming ions, we are only ever gaining or losing electrons, never protons. Protons will always stay the same. Very important. So this means there are more electrons than protons, and because of this, anions have an overall negative charge. A chlorine atom turning into a chlorine ion. So what I'm seeing on this, chloride ion. If it's an ion, if it's an anion, if it's a negatively charged ion, it'll end with IDE most of the time. We'll do examples with this as well, don't worry. So on the left here I have my chlorine atom, and it has 7 outer shell electrons, or in other words, it's got 7 valence electrons. Atoms want to attain a noble gas configuration. In other words, they want to have a complete octet. In other words, they want 8 electrons on the outside. Almost always they want to get to 8 electrons on the outside. And we see that here. We can see that because this chlorine has gained 1 electron, giving it 8 electrons on the outside. This is called an octet. I will explain this in the next slide. I'm just trying to preview this coming up. So now, since it's gained 1 electron, that means it has 1 more electron than protons, which means it's now negatively charged. Stable octet, I told you I'd teach you about it. Here it comes. Okay, so what this is this is when the valence shell is full. And most of the time, that means we've got 8 electrons. When the valence shell is full, the atom or ion is stable and it's going to be much less likely to react. The example are going to be noble gases. If you don't remember what noble gases are, if we got a periodic table and it looks like this, oh, that's a good one. That's a nice looking periodic table. The noble gases are this last column on the very far right. These are our noble gases. And what they have in common is that they all have a complete octet. Atoms tend to react in a way that would lead to them having a stable octet. When ionic bonds are formed, here, actually stop. Let's stop, rewind. Let's translate this. That just means 8 electrons on outer layer. Outer shell. Let's try to stay consistent so we're not being confusing, Mr. Parks. That's a great idea, Mr. Parks. Thanks, Mr. Parks. Okay, so that just means 8 electrons on the outer shell. When ionic bonds are formed, 2 atoms will exchange electrons. That really just means one gives and one accepts. This one atom. Now, it doesn't always mean 1 electron. We can have multiple electrons being donated and accepted, but one will give an electron away and the other one will accept it until we get to the stable octet. This will cause opposite charges. Oops. This will cause a creation of cations and anions. You guys will notice very soon here, I'm not a good speller. I know what I'm trying to say, I just can't spell the words I need to spell. So the opposite charges between the cations and the anions cause a very strong attraction. What you should be thinking about here is these are just like opposite ends of a magnet. I would strongly encourage you to start to think about chemistry and specifically atoms and ions as tiny, tiny, tiny little magnets. And these little magnets will either cling together or they'll push away or they're going to kind of get close to each other based on how strong of magnets they are. It's a really good trick to help you think about these things that we can't really see yet. So since they are oppositely charged, that means they are oppositely charged ions, and hence the name we get an ionic bond. An ionic bond is just 2 oppositely charged particles attracted to each other. A positive and a negative being attracted to each other. All right, let's start doing some ionic bonding, right? Sounds like fun. I'm excited. Important things to remember. We need to know, in order to predict if something is going to be a cation or an anion, if it's going to gain electrons or lose electrons, we need to know what how many valence electrons something has. So what this is these are just columns out of the periodic table. I know this looks a little goofy when it's presented this way, so what I'm going to do is just turn it into something that makes a little bit more sense. If this is the periodic table, we're just looking at columns 1 and 2, this column, and this column, 13, 14, 15, all the way up to 18. So what we are really doing with this slide is we're ignoring this middle piece here. We're ignoring the spot of the periodic table or where it drops down. We're just looking at the outer edges. So what I'm hoping you'll notice is if it's in the first column, all of these elements, all of these atoms, meaning they're neutral, have only one valence electron. If it's in the second column, and I know I blocked the 2, they are going to have 2 valence electrons. 2, 2, 2. And then the pattern holds true with columns 13, 14, 15, 16, 17. You just ignore the 10 in front. So if it's in column 13, that means it's going to have 3 valence electrons. 14 will have 4. 15 will have 5, and so on and so forth. So we're going to have to start to use the Lewis dot structure to deduce whether something will gain or lose electrons. It's a good little preview to think about these as paired electrons and unpaired electrons for future parts of the bonding section we have coming up, the covalent part. But for right now, this is just a little preview. The most important thing that you should be asking yourself for ionic bonding, so this is for ionic bonds, you should always ask yourself this question. Is it closer to 8 or 0 valence electrons? That will be the key. And I'll keep asking myself this with every single time we do the practice problems, and you'll see what I mean. All right, so this is a review. Elements that do not have a complete octet tend to react, meaning they will want to gain electrons or lose electrons to have a complete octet. In order to predict bonds, you must find the reacting elements on the periodic table first. So you got to figure them out. And then when you find them, what you really need to know is how many valence electrons. That's the key here. And then when the elements react, bonds are formed. One electron will be given away, and that will become a cation. Something will accept that electron. It will become an anion. We will have 2 oppositely charged particles. They are going to be attracted to each other, and they're going to form a bond because they are attracted to each other. Bonds that are formed by transfer of electrons from one element to another. This is the definition that we're going to be using for ionic bonds. It's going to be a complete transfer, a complete giving away. A good example is if somebody gives you a present, they give it to you, and it's yours. They have transferred it to you. They don't give it to you, and then they don't ask for it back, and then they'll give it to you and ask for it. No, it's a one-time, here's a present. Take this. I want you to have this. And then you say, oh, thank you. You're so nice. We should be friends. Oh, look, you guys just formed a bond. Friendship is a type of bond. Not a chemistry type of bond, but you know what I mean. Each element is now an ion, will have a complete octet after the transfer of electrons. Here is an example. So what I'm seeing here is lithium has 1 valence electron. Oops, misspelled valence. And fluorine has 7. valence electrons. So I'm going to ask myself, is lithium, is this closer to 8 or 0? And I know just based off of, let's fix that. That looks really bad, Mr. Parks. 8 or 0 electrons. I know based off of numbers that one valence electron, the number 1 is closer to 0 on a number line than it is to 8. This is just numbers, okay? So since lithium has only one valence electron, it's going to be much easier for lithium to give away that 1 electron than it would be for lithium to try to gain 7 more electrons. So then what lithium will do is, since it's closer to 0 electrons, it gives. Since fluorine is closer to 8 electrons, it accepts electrons. So then what I can see here is this lithium will give its electron to this fluorine, and then we get the picture off over here on the right. Lithium has lost an electron. Therefore, the number of protons now is going to be greater than the number of electrons. Therefore, it is a cation. Fluorine, on the other hand, has gained electrons. Therefore, the number of protons is less than the number of electrons. Therefore, it is an anion. Just so you guys know, this little three-dotted triangle means therefore. And so you guys know therefore means so I know that. It's like you can figure it out from that. So in an ionic bond, the electrical force of the attraction between the oppositely charged ions is what causes them to be bonded. One is positive, one is negative, opposites attract, and they are now bonded together, like you and your friend who gave you that present. The formula unit, a chemical formula, shows the whole number ratio of the atoms and ions in an ionic compound. So if we look at the Li plus and F minus, since we only needed 1 electron donated, lithium only wanted to lose 1 electron, and fluorine only wanted to gain 1 electron, those two things are like perfect for each other. So they react in a 1-to-1 ratio. So for every 1 lithium, I only needed 1 fluorine for both of them to achieve the stable octet, to have this complete outer shell. So then the formula unit for lithium fluoride would have been LiF. Important things to know. When you're writing this, cations come first. So it should always go the positive ion and then the negative ion, whatever it is. And you'll see me do that in the next couple slides here when I do some practice problems with you guys. Cool. All right, so now we're going to do an Na and F, sodium fluoride. So first step we need to do, first, find on the periodic table and figure out how many valence electrons they have. So I'm going to do that. Sodium is in column 1 and fluorine is in column 17 or 7, depending on what periodic table you're looking at. So what that means then is sodium has 1 valence electron, fluorine is going to have 7 valence electrons. I know that sodium is this 1 valence electron is closer to 0, therefore it will lose 1 electron to get to that outer shell, that stable octet. Fluorine has 7 valence electrons, which means it's closer to 8. It's closer to filling up its outer shell with 8 electrons than it is to losing it. So then it's going to want to gain 1 electron. And the reason why I know it's going to want to gain 1 electron is because from 7 to 8, it needs 1 electron to get to that final little bit. So if you're following along, the second step is going to be, how will electrons move? So in this situation, our electron will move from sodium. Sodium is going to want to lose its electron, and it's going to go to fluorine. Fluorine was going to want to gain that electron. So when this reaction is done, we are going to have Na with a positive charge, and we are going to have fluorine with its newly gained electron. I'm going to keep it in the same green color that sodium is in, because we can see then that that electron went from sodium to fluorine. Fluorine pulled it away from sodium. Fluorine is now a negative charge. So now the last thing that we got to look at is, I wanted to keep the colors consistent. The last thing we want to check out is we need to move electrons until everything, or every particle, I'm going to say, has a stable, oh, I missed a couple letters there. Oh no, I just missed the B. It's not too bad. Okay. A stable octet. So sodium has 0 valence electrons now. Fluorine has 8 valence electrons now, which is overall happy times for both of these. So then what we end up getting is a new compound that is going to be NaF. Our name is sodium fluoride. Things to notice: the name and the formula compound unit. So this would be the name, and this would be the formula. Both go cation, then the anion. So since fluorine turned into a negative particle, that's going to go in the second part of both the formula and the name. Since sodium was a cation, that will be in the first part. You'll see the pattern continue. We're going to do 2 more of these together, and they're going to get a little bit trickier. So this one is going to be aluminum chloride. So first step, find on periodic table. So this is in column 3 and 17, which means aluminum has 3 valence electrons and chlorine has 7. 7 valence electrons, therefore it will want to gain 1 electron, because if it gains 1 more electron, it'll want to get to 8. If it gains 1 more electron, it will have 8, which will have that stable configuration. Aluminum has 3 valence electrons. 3 is closer to 0, so what that means is aluminum is going to want to lose its electrons. So then what we get then is it's going to want to lose all 3 of its electrons. So I picked this example because I wanted to show you guys that it's not always 1 electron. Sometimes you can lose 2 electrons. Sometimes something can lose 3 electrons. The only thing that will change is the ratios that you end up needing. So what I want to do then is show you how this works. And this slide's going to get a little cramped. So I'm going to put up a wall and start to show my ions being formed on the right here. So I've got an aluminum. And I have a chlorine. Aluminum wants to give electrons away, and chlorine wants to gain them. Chlorine can only take 1. So what's going to happen is chlorine is going to accept that 1. Aluminum still needs to lose 2 more electrons. So what will happen then is another chlorine will come along. So this chlorine, oops, let's fix that dot. That looks kind of goofy. Another chlorine is going to come along to accept yet another electron from aluminum. Aluminum still needs to lose another one. So then a third chlorine is needed. You're going to do this pattern until everything reaches noble gas configuration. So then what I end up getting is, I'm going to put up another little wall. I end up getting 3 Cls, 3 chlorides, that have now gained that extra electron from aluminum. Boop, boop, boop. And now they're all negatively charged. And my aluminum now has lost all of its valence electrons. In fact, it lost 3 valence electrons. So if you're losing 3 electrons, that means there are now 3 less electrons than protons. There are 3 less negative charges than positive charges. Another way to think about this is, since you lost 3 negatives, there are going to be 3 more positives than negatives. So there are now, for aluminum, there are 13 protons and 10 electrons. In other words, it's going to be a positive 3 charge since it gave 3 away. So our formula will be Al, Cl, and since I needed 3 chlorines, I'm going to say that down here. I needed 3 chlorines. You need to take that number, and it's on the lower right. It's like an exponent, but below. So it's a little bit different than math, but it's the same idea. Scratch that. Don't think about it like that. That's a really bad example. Sorry. All right, we're gonna make one that's a little bit harder. This is about the hardest it'll be on the next one. All right, so this is going to be one of the hardest examples. The steps still remain the same. It just takes a little bit more work. So first, find them on the periodic table. Figure out what column they're in, what group. So column 2 and 15. So calcium has 2 valence electrons, and nitrogen has 5. So what I know from this is calcium has 2 valence electrons, therefore it's easier for it to lose 2 electrons, just because it's closer to having an empty shell than a full shell. Nitrogen has 5 valence electrons, therefore it's 5 is closer to 8. So what that means is nitrogen is much more likely to gain electrons until it has a full shell rather than it losing electrons to be empty. So if your valence electrons are closer to 8, that atom will gain electrons until it's full, until it has a complete shell. And if your valence electrons are closer to 0, it will lose electrons so that it has an empty shell. So since nitrogen has 5 valence electrons and it wants to get to 8, it will gain 3 electrons. All right. This is where things start to get really kind of gross. Let's just sequester that over to the side. I'm going to start to draw all of this out by showing the electrons moving around. So there's my Ca. Here's my nitrogen. I know nitrogen wants to gain electrons and calcium wants to lose electrons. So I'm going to start to move them over. So this one will go there. And this electron I'm going to put on the other side over here, which means calcium gave away its 2 electrons. So calcium is okay. But nitrogen still is missing 1 electron on the bottom side here. It still has this opening for an electron. So then, in order to satisfy that, a second calcium will come along, which can donate another 2 electrons. So then this calcium will complete the octet of that nitrogen. But now this calcium has another electron that it wants to give away somewhere, but it doesn't have anything to donate it to. So then a second nitrogen will come along. 1, 2, 3, 4, 5. Oh, that's good. So now that calcium's okay. It was able to give away its last little electron. But now this nitrogen still needs 2 more electrons. Are you starting to notice the pattern? It seems to be never ending. So this still needs 2 electrons there and there. So what we need then is another calcium, something that's going to be able to donate more electrons to this picture. So a third calcium will come along. And then this will donate its electrons. There and there. I know this looks really kind of confusing, so I'm going to redraw this on the bottom. So what I have then is 3 calciums, and every calcium lost 2 electrons. So since it lost 2 electrons, that means it's going to be positively charged because it lost a negative. And all of these will become 2 plus. We had 2 nitrogens that we ended up using. And they both came with 5 valence electrons to start. And each of them gained 3 electrons from calciums. Two, 3. So since these nitrogens gained electrons, That means they are now anions with a 3 negative charge. So I'm going to just stop and double check everything is good here. So all of my calciums have 0 valence electrons, which is what we are hoping to achieve. So the calcium 2+ ions, those cation ions, those are okay. My nitrogens, they all have 8 valence electrons. So those are also okay as well, because remember, every ion is trying to get to either 0 valence electrons or 8 valence electrons. So nitrogen gained electrons until it got to the 8 valence electrons, and calcium gave those electrons away until it was able to get to 0 valence electrons. Oh, so this is pretty okay for right now. Now let's do our formula. Remember, cation comes first, so my calcium is positive. So it goes Ca, and I have 3 calciums, so I'm going to put a little 3 below it. And I have a nitrogen, then there were 2 of them, so Ca3N2. I'm going to just write it in a single color now so that everything looks nice. This is one of the hardest examples, just because it keeps going on and on and on. What I'm hoping you guys noticed is that the logic never changed. We are still losing, something is going to lose electrons until it has 0 valence electrons. Another species, another atom, will gain electrons until it has 8 valence electrons. So it's this pattern. Something will lose all of its electrons, all of its valence electrons, and the other thing will gain valence electrons until it has a full shell. Oh, here is just a list to help you start to make a little bit of sense out of things. What I do want to highlight is this: hydroxide, nitrate, not to mention sulfate down here. Oh, my pen's not working. Carbonate and hydrogen carbonate. These are called polyatomic anions. I'm going to break this down into its parts. Poly. What that means is, like, if you have a polygon, that's just a shape with many sides. So this just means many. Then we have the word atomic. That just means atoms. And then we've got the word anions. This is just negatively charged. So what this just means is, if you have a polyatomic anion, it just means it's a single thing made of many atoms, and it's an anion. You'll notice on the left side, the cations, there is something that is a polyatomic cation. So there is one of our cations on the left side of this column that is made out of more than one element or more than one atom, and it's a cation. If you're still looking and you can't find it quite yet, I'm going to highlight it for you. And it's right here. It's this ammonia. It's made out of 1 nitrogen and 4 hydrogens, and it has a positive charge. Something else that is going to be worth noting, and I'll practice this with you guys a lot, so don't worry, this is something we're going to focus on, is sometimes things can have different charges. So for example, iron can have 2 different charges, and when that's the case, we will tell you what the charge is. Iron 2 just means it's positive 2. Or if it's iron 3, these are Roman numerals, means it's 3+. This is one of the trickier things. So we'll spend time in class really practicing this, make sure that we really got this down 100%. We're almost done, guys. We're almost done. So the reason why we call this for example, NaCl, the reason why we call it a formula unit is because ionic compounds have a lattice arrangement. What that just means is it's very highly structured. And it's ordered and locked in a very specific arrangement. So it's not like a sodium is next to a sodium is next to a sodium and then 15 chlorines in a row and then another sodium. It's not random. It's not random at all. You can see the pattern. You can see the, let's go black. You can see there's a continuing pattern of sodiums next to chlorine, next to sodium, next to chlorine, next to sodium, next to chlorine, next to, it's a pattern over and over and over. It's NaCl, NaCl, NaCl. So a formula unit just means it's the same pattern repeating over and over. And a lattice structure just means it's like a big block. It's like just a bunch of Legos put together to make a single block. We're almost done. All right, properties of ionic compounds. They have a lattice structure. We just saw this. Ionic compounds, since they are oppositely charged ions, their attraction is incredibly strong. And since it's incredibly strong, it's going to lead to two main properties. One of them is it's going to have a very high melting point. A lot of these things melt in the thousands of degrees Celsius range. So you have to get it really hot before they turn into a liquid. So since they have high melting points, that means they are going to be solids at room temperatures. And also, since they're very attracted to each other, these are hard substances. You can think, I guess not really a rock. Just think about salt. If you have a piece of salt, a grain of table salt in your hands, you can't crush it. It's just too strong. Ionic substances, since they're oppositely charged, what that means is they can dissolve in water. Water is really, there are two halves of water. There's a positive half and a negative half. The hydrogens are kind of positive and the oxygen is kind of negative. So water is able to latch on to the oppositely charged parts of the lattice and break it apart. It's a lot easier for me to draw this out for you guys and explain it in person, so I'll do that. And then also, when the ions are free from their lattice structure, so when they're not in this block shape that we just saw. So, for example, when they're dissolved in water or when they're melted, what that means is those ions are free to move around and then they can conduct electricity. And then since in a solid state they have a lattice structure, those ions are not free to move around. They're locked into place. They're next to their neighbors because they are too attracted to their neighbors. And since they're locked in place, they cannot conduct electricity. Remember back when you guys studied metals and properties of metals, it should have been last year. Metals conduct electricity because electrons can move through them. In a lattice structure, these ions cannot move, so then they cannot conduct electricity. Electricity is a moving of electrons. So in order for something to conduct electricity, it needs to be able to move, and the lattice structure does not let the ions move when it's a solid. So when they are solid, they cannot conduct electricity. Whew, a lot of information, a lot of information. I hope you guys understood most of it. Have a good day.